Hello, and welcome to what should be Lesson 11 in Engineering Fluid Mechanics in CE 3305. So this is largely Chapter 5. So this is a chapter called the Control Volume Approach. And so this is the first of several discussions that are going to be on the Control Volume Approach. It's actually worth taking a little bit view of parts of the book to see where we're going. So the prior 2 or 3 videos we're dealing with these concepts of flow rates, where there's a cross-sectional area of flow, a mean section velocity, and that velocity multiplied by some time interval produced dimensions of a volume, and so the amount of volume per unit time is what we call the flow rate. Usual symbol is Q. There we go. Let's get some focusing going on here. Well, you can actually see that now. And as we just did, Q is equal to the integral of the area of the velocity inner product with the area, and alternatively, the definition of average or mean section velocity V bar is Q over A. We did the same for mass flow rate already, and now we are to the control volume approach, and the idea of the closed system and a control volume. Again, the book does a really useful sketch where it shows a fixed amount of mass, and this piston is compressing downward, and so while the mass doesn't change, the system boundary or the volume does change. That would be a closed system. Another approach is to fix the volume in space. We don't let it change, and we keep track of what comes in and leaves that volume. And that fixed volume in space, also known as an open system, is the control volume. Then there is a nice chart on different ways we can analyze things. You'll notice down at the bottom here, intensive and extensive properties has earned its own subsections, so clearly they're going to be important. And in fact, they are. We're going to spend a little bit of time relating control volume behavior to fluxes that are crossing the boundaries of the control volume. And ultimately, this is the main tool we use. The really astute reader and student of mathematics will notice as we get through this that it looks a lot like Gauss's divergence theorem, because it is. Okay, and so the general thing that we're after is right here. We're coming up with a way of relating the behavior of an extensive property of a closed system to intensive properties at the control surface as well as within the control volume. So Reynolds transport theorem is really a tool named after Osborne Reynolds of Alcoa aluminum fame. No, that was a terrible pun. To relate behavior crossing a fixed boundary in space with what's going on in the volume. Hence the name control volume. Okay, let's see, I'll bust this up just a little bit. Yeah, that's better. So, the control volume for a lot of the work in the remainder of the class is going to play the role that a free body diagram plays in other engineering mechanics, either statics or dynamics. So I've just drawn a rectangular chunk of space. We'll give it finite dimension, so it'll be delta x unit coming out of the paper, delta z units tall, delta y units long. Here's my coordinate system. X, Y, and Z. And this cube really right now isn't terribly super interesting. It has 6 faces, and if we're just taking a look at this face, take a small piece of it, consider just that little bit, we can associate the magnitude of that area as area, and we can have a vector which we'll call the area vector, and there's the differential area vector. So the key things why I drew it as a vector is that by convention the outward pointing unit normal or outward pointing area vector is just that. It points outward from the control volume. So an equivalent differential area on the top would point up, equivalent one here on the right would point to the right, one here on the left we can't see would point to the left, bottom would point down, and so on. So all those vectors are pointing out. So as of right now we have a control volume is some defined volume in space. Okay, the bounding surface. So the surface of this volume, I'm going to shade it in green, at least the surface that we can see. So the bounding surface is called the, wait for it, control surface. There are probably other names in the literature, but that's what I'm going to use. And what the control volume is going to allow us to do is apply Reynolds transport theorem, which in turn allows analysis to move from Eulerian reference frames rather than a Lagrangian reference frame where we have to keep track of individual particles. And the goal for today is to set up the conditions to be able to describe the fundamental laws of mechanics, conservation of mass, momentum, angular momentum, energy in integral form. So rather than differential form, integral form. Okay, so dA, we've already said, is the outward pointing area vector. And if we were to introduce a Cartesian coordinate system with unit basis vectors. So dA of the back is going to be minus delta y, delta z in the I direction. dA in the front, delta y, delta z, the plus I direction. So this dA for a small differential thing is taking on those values. dA left minus delta x, delta z in the j direction. dA to the right is delta x, delta z in the j direction. dA bottom minus delta x, delta y, k direction. dA the top, delta x, delta y in the k direction. So those are our 6 faces of that little teeny cube. Okay, so the principal idea is that we're going to try to express in integral form the conservation of mass If you recall from your other mechanics classes, the conservation of mass is simply the time rate of change of mass of an entire system is zero, or mass is conserved. The conservation of momentum simply says that the rate of change of momentum, of linear momentum, so the mass times the acceleration is equal to the sum of the forces on the system. The conservation of angular momentum says the mass times the angular acceleration of the system is equal to the sum of r cross f, the cross products of the basically lever arm vector and the force vector. And the conservation of energy in a system that simply says that the rate of heat flow into a system minus the rate of work done by a system on its surroundings is equal to the rate of change of energy in the system. And the last one is entropy. It says the time rate of change of entropy for the system is greater than or equal to 1 over the temperature multiplied by the rate of heat flow, by the change in the rate of heat flow into the system. Okay, so entropy, we're not going to look at it in this class. Conservation of energy, we will special case that where we can, and the other three we'll go into in some detail. Okay, so to use the control volume approach, the system equations need to be converted into volume variation equations. Again, we revisit the idea of extensive property and intensive property. So to use control volume analysis, we need to convert system equations into volume variation equations. I am not sure that terminology is exactly mathematician satisfactory, but it's going to suffice for now. Remember the extensive property and intensive property are going to play a role in here. Extensive property is a property that's distributed throughout an entire mass of a fluid, or think of it as a system property. And an intensive property is the amount of property per unit mass. And the intensive properties are going to be more like volume variation properties. I think this will make sense shortly. Okay, so let's consider an extensive property of mass. Usual symbol is m. Mass per unit mass is going to be m over m, and it will equal the lovely value of 1. Mass per unit volume is mass over volume, and we've been calling that rho. So the fundamental relationship between extensive and intensive properties for a system is given by what's going to happen on the next page. Sound effects. B of a system, where B is some extensive property, is equal to the integral of the intensive property, as long as the intensive property is expressed per unit mass, with respect to mass, which in turn is also equal to the integral of beta rho d volume. So here's what's going on here. The differential mass is going from mass per unit mass to mass per volume, and so we have the rho dV. So these three statements are just saying those different letters of the alphabet. You can put equal signs between them, and that's all good. Okay, so we can express from an entire system to property per unit mass times mass, or property per unit mass times mass per volume times volume. So let's just take a look at that with respect to mass. Let's suppose our intensive property of interest is the mass per unit mass, which is beta. We're going to multiply that by rho, which is mass per unit volume. And then we're going to integrate that with respect to volume. So let's see what we have left. We have mass per volume integrated by volume, which is going to equal, because the volumes essentially cancel, all we have left is mass, which is what we expected. All right, so in this equation up here, or this relationship, is the fundamental relationship for Reynolds transport theorem and producing our integral equations of fluid flow properties. I can return to my block. So here I have a block of material. If I had a brown pen, I would color it brown, but I'm going to have to use blue. And you ask yourself, why would you color it brown? Because there's a wonderful place outside of Bakersfield, California called Brown Material Road, and that's where all brown things come from. I think it's actually a name change from what the oil workers out there used to really call it. We'll introduce our coordinate system as before. Let's see, X, Y, Z. And this blue thing has some fixed value of mass. And we're at some moment in time t, and so we're going to surround it with a control volume. It's easy to do. I'm just going to draw little dashed lines on it to represent a control volume. So there's my control volume, completely containing the thing. It's supposed to be actually totally equal to the thing. I've got to put some space here so we can see what's going on. Okay, so there's my control volume. This is my control volume, and this is all at time equals some moment in time. All right. We'll assume that this mass is moving in a velocity field, and that velocity field is defined as v is equal to v of x, y, z in time. And somehow presume that we know what it is. And at time t, at this moment in time, that mass is completely enclosed in the green volume. Okay, now we're going to draw things again a short period of time later. So I'll show you how I'm going to do this. I'm going to go ahead and so here's my control volume. Remember, the control volume is a fixed volume in space. So at any time we look at it, it's always just this green In this case, a parallelepiped, think of it as a green cube. Okay, so there's your Borg cube. Now, let's suppose that the mass is translating strictly to the right, and that's simply a matter of, it's not a matter of necessity, but it'll make the drawings a lot easier. I think you'll see the point. And so at some short period of time later, the mass is propagated to the right, so now I'm going to draw the mass. Black line's blue. And here's my mass a little bit later. It's blue. Hey, it's a blue mass group. Coordinate system is not changed. This is now at time t plus delta t is the short time interval. So when I examine this picture, I can identify three zones. I have zone number 1, which is the part of the control volume that used to have the blue mass in it, and now that blue mass has left. Part number 2, which is part of the control volume that still has blue mass in it. And then part number 3, which is exited the control volume and has blue mass in it.